Welcome to This Explainer. Okay, so large language models have obviously taken the world by storm, but behind the curtain of this incredible technology, there is actually a fundamental flaw, like a real structural limitation in how these models generate text. Today, we're tackling one of the most fascinating bottlenecks in modern AI. We're going to explore exactly what this bottleneck is, and more importantly, how the absolute brightest minds in AI research are trying to fix it. Let's dive right in.
So, how many R's are in strawberry? You've probably seen this famous glitch online. Highly advanced AI models will consistently miscount the letters in such a simple word, stubbornly insisting that there are only 2 R's. But why? How can a model that writes sophisticated Python code and passes the bar exam fail at basic character counting? Well, the answer actually lies in the very engine of its generation.
And that glitch illustrates our core issue. As Andrei Karpathy points out, tokenization creates what he calls a spurious layer. It's essentially a disconnected barrier between human ideas and AI processing. You see, the AI doesn't see human letters or words the way you and I do. It sees fragmented, disconnected subwords, or tokens. It is literally blind to the actual spelling of strawberry because the word gets chopped up into arbitrary chunks before the model even gets a chance to look at it.
Which brings us to the main antagonist of our explainer today, next token prediction, or NTP. This myopic left-to-right guessing game has some massive flaws. First off, greedy generation and error accumulation. Because it only optimizes for the very next token, a tiny mistake early on just compounds into a massive hallucination later. Second is granularity mismatch. We humans, we think in high-level ideas and sentences, but NTP forces the AI to process information in tiny, rigid subword chunks. Third, compute inefficiency. Because of quadratic attention, the model has to look back at every single previous token for every new token it generates, which, as you can guess, is incredibly expensive. And finally, misaligned supervision, through a process called teacher forcing, where the model essentially learns to just guess plausible continuations instead of actually learning how to plan ahead.
So how do we fix this? Well, here is our roadmap for today. 1. The next token trap. 2. Predicting blocks and plans. 3. The continuous generation shift. And 4. Radically new AI architectures.
Let's start with number 1, the next token trap.
Look at this number, greater than 99%. This highlights a really fascinating paradox in modern AI. Models like Gemini 1.5 can hit greater than 99% accuracy on these needle-in-a-haystack tasks, meaning if you hide a single obscure fact in a massive book, they'll find it perfectly. Yet these exact same models consistently fail to maintain global consistency in long-form summaries. They just lose the plot. Why? Because think about it. You cannot write a coherent novel if you're only allowed to think one word ahead at a time. This autoregressive framework creates illusions of deep intelligence, but fundamentally prevents global planning.
But hey, there's a silver lining here, and it's something I find absolutely incredible. Research actually shows that larger-than-token representations exist inside transformers. Studies reveal that the middle layers of a transformer are genuinely anticipating multiple future tokens and forming complex, high-level concepts. The model's brain is actively planning ahead, but it's physically bottlenecked by its mouth. It's forced to spit those brilliant, complex plans out one tiny sequential subword at a time.
All right, moving to number 2, predicting blocks and plans.
So let's look at the first family of solutions here, multi-token prediction, or MTP. This is where we change the prediction target from a single token to a block of multiple future tokens using a shared context trunk. So instead of guessing just token number 5, the model guesses tokens 5, 6, 7, and 8 all at the same time in parallel. It slightly breaks that strict chain rule of next token prediction, and we're actually already seeing it deployed in cutting-edge models, like DeepSeek V3, to accelerate things and encourage way better short-term planning.
And does it work? Absolutely. To put that into perspective, research by Gleekle and his team showed that by simply training a 13 billion parameter model with multiple MTP heads, they achieved up to a 17% higher accuracy on the MBPP coding benchmark. So not only did it make the model smarter by forcing it to plan ahead, but it also gave a 3x speedup in decoding. That is a real game changer.
The second family in this looking ahead category is Plan Then Generate, or PTG. Think of it like writing a book. You wouldn't just sit down and start typing word by word with zero idea where the story is going, right? You'd write an outline first. Well, PTG models do exactly this. Step 1, generate a high-level abstract plan from the context. Step 2, generate the final output sequence based on that plan. Models like Planner use this approach to ensure the final output stays globally coherent.
It acts as a structural guide before the token-by-token generation even starts.
That brings us to number 3, the continuous generation shift. Now we're shifting away from sequential tokens entirely. Under the old autoregressive paradigm, the AI generates token by token locally. It's kind of like laying train tracks while you're standing on the front of a moving train. If you lay a bad piece of track, you can't go back, the train derails. But the new continuous generation paradigm, it initializes the entire output simultaneously and refines it globally in parallel. It's like sculpting a statue out of a block of clay. You get the rough shape of the whole thing all at once, and then you iteratively refine all the details together.
So this brings us to our third overall family of solutions, latent reasoning models. These models shift autoregression into a continuous latent space. Instead of operating on sub-words, the AI thinks in semantic units. We're talking entire sentences, thoughts, or abstract concepts. For example, large concept models, or LCM, generate one concept vector per sentence. Another mind-blowing example is Coconut, which enables latent chain of thought. The AI literally refines abstract, continuous concepts in a hidden thought space, exploring multiple trajectories before it ever bothers translating those thoughts into rigid text.
Building directly on that is our fourth family, continuous generation approaches. Here, text emerges through parallel, iterative refinement across the entire output window. This includes diffusion-based models like Mercury or block diffusion, which actually start with noise and iteratively denoise it into coherent text, very much like AI image generators do. It also includes flow matching, which maps out deterministic trajectories from noise to text, and energy-based models, which score entire sequences holistically and use gradient descent to find the absolute best overall output. Boom! No more left-to-right bottlenecks.
And finally, number 4, radically new AI architectures. This leads us to our fifth and final family, non-transformer architectures, or NTA. By definition, these models inherently sidestep token-by-token autoregression through entirely different core mechanics. Basically, they don't even try to fix next token prediction. They just make it completely obsolete by changing the fundamental way the AI processes sequences. What does that actually look like? Well, we are seeing two massive breakthroughs here. First, state space models, or SSMs, like Mamba. Mamba tracks sequence information using continuous signals, scaling linearly instead of using that incredibly expensive quadratic attention we talked about earlier. Second, we have joint embedding predictive architectures, or JEPAs. Models like LLM JPA completely stop predicting raw text. Instead, they predict high-level semantic compatibility. It learns by making sure a text description in a piece of code actually match in meaning, rather than just playing a game of guessing the missing word. So, to bring this whole shebang together, here is the complete taxonomy of how researchers are systematically tearing down the walls of the next token trap. We've got multi-token prediction, pulling blocks of tokens at once, plan then generate, organizing thoughts before speaking, latent reasoning, thinking in continuous semantic spaces, continuous generation, sculpting text in parallel, and finally, non-transformer models rethinking the mechanics of AI completely. It's a massive shift away from legacy AI generation. I want to leave you with a provocative question to ponder. Does true artificial reasoning require abandoning human language tokens altogether in favor of pure latent thought? Because, as we've seen today, human words might just be a little too rigid and fragmented to serve as the internal operating system for an advanced AI. Maybe the future of artificial intelligence lies beyond human words entirely. Thank you so much for joining me for this explainer. Keep questioning, keep learning, and I'll catch you in the next one.